Hello there. Today we'll be doing edit distance. This is a pretty unique problem. Number 147. Oh my gosh. We're three more away from completing this. So let's see. So edit distance is that we are given two words. We are given three options. Either insert, delete, or replace a character. All right. So let's suppose that we have horse and we have horse. And if the two characters are different, that means that we have to do one of the three operations, which is insert, delete, and replace. So since they're different, we could try replace, and this would mean that we move both forward. So if we have pointers, we have I plus 1 and j plus 1. If we delete, that means we're gonna skip this one and try the next one. That means that I is going to remain the same, j plus 1. And if we're going to insert, that means we're going to insert an item and here. And that means we can basically move, delete is I plus 1, j plus 1, because we're moving the one forward, so we're skipping that one. And we are, hold on. Deleting the item and remaining at the same place. But if we're inserting, that means that we are, we have that item. That means we just added the A in, and then we stay at the H. Those are our three operations. And once we get those operations, we check the next one and they're equal. Let's say we replace. If they're equal, that means we don't have to proceed with an operation. So this equals this particular item plus 1 operation, and otherwise we just move, which is a plus 0, I plus 1, and a j plus 1, which is plus 0 operations. And those are our three options. And once we can just, this is a DFS call, similar to the previous problem that we've done. This problem is called distinct subsequence, and we did this earlier, the previous video. Basically, it's exactly the same, more or less. With this one, we only had the option of, moving, taking it or not taking it. But this is not taking it. This is move, and not taking it is basically we're gonna just do a delete, right? Yeah, pretty much. Okay, so anyways, with that, we are able to get the same item and we're done, good to go. But if we are done early, let's say we're just trying to get AR, and we have gone up to here, that means that we can return the remaining characters if they're already equal. So yeah, so that means no characters at all. Yeah. So let's make that more clear. Let's say we have 0 characters, right? For J, and we reach the end. That means we have inserted all of them. That means we can return length of word 2 minus J, which is 0, which is 5. I don't know if that made sense. Okay. I think it will make more sense as we do the problem. Okay, here we go. So let's set up the DP is equal to empty dictionary, and we're going to take the key as an I and J, and what the value is going to be the minimum number of operations for that particular location, DFS of I and J. Of course, we're going to pass back an int, and if I is equal to the length of word 1, so So basically we reached the end. We're gonna return the length of the word 2 minus j. That means those that we have matched all the items except these two, so we have to delete them now. Right? So basically, if we reach the end of HORSE and we have more left, that means we have to delete everything. Delete 2 more items. Else if j is equal to length of word 2, then that means we're going to return length of word 1 minus I, basically the number of items we have left to delete, that we have reached the same number of items. Else if the item is already in the DP, that means we can return DP of this I and j tuple. Else that means it's none of the base cases, and we need to return word 1. If they're equal, that means we can do a move. So a move would mean that will result is equal to a DFS of I plus 1 and j plus 1, and DP of course, we can do a DP of result ij is equal to result, and then we'll return the result afterwards, because we have one more step. That is, if they're not equal, result is equal to the min of basically 1 plus DFS of I. Well, we're not going to do that first. We're going to get the first one. DFS of insert. So this is I and j plus 1. Result is equal to the min of results and I plus DFS of I plus 1 and j, which is to delete. And result is equal to min of results of 1 plus DFS I plus 1 and j plus 1, which is the replace. And lastly, we can set this to results and return. With that, we can return the DFS of 0 and 0. And let's give it a shot. Looking good, and let's submit. Okay, this is a very fast solution, it looks like. And we got a pretty good memory score. It looks like this is a top-down approach, DFS. And I think it's much cleaner than the bottom-up, which requires a lot of memory allocation of writing up a lot of squares and defining all the locations about what is what. I think we can do this more verbally rather than managing memory, so I think it gets the idea across better. Anyways, if you have any questions, please comment below. If you enjoyed the video, like and subscribe. If you want more videos, check the link in the description below. And that's all. Okay, I'm gonna just do a review right now, and because I skipped that. So basically, we created a DP to store the items so that we can get them again. The O of n is O of n. The runtime is basically n times m. Basically means the length of word 1 and word 2. We're gonna go through every single one item, and we're gonna do a DP of each. Why is that the case? Because well, it's times 3. Of course, we're doing 3 DFSs. But that means we just need to operate on a single item once, and then we never have to operate on it again. Anyways, yeah. This is O of n times m space because it's recursive, and it's everything stored in memory. Yeah. Anything else? No, I think that's it. If you have any questions, please comment below. Thank you very much, and I'll see you in the next one.